So now we're going to derive something called the lever rule, and basically this will allow us to visualize how the fractions of a system in terms of vapor and liquid for a substance change over time as we apply pressure to the system. So we'll start off with our equation from before. FZI equals Vyi plus Lxi, and we know that F equals L plus V. So substituting L plus V in for F, we have L, and I'll skip a step here, but Lzi plus Vzi is going to be equal to Vyi plus Lxi. And then from here, we want to isolate the terms with the coefficient of L and the coefficient of V to their own sides. So we'll say Lzi minus Lxi is going to be equal to Vyi minus Vzi. And then we can move the L and the V out of those terms. And then if we want to divide V by L, we have to divide this across and then divide that back across. So we'll end up with V over L is going to be equal to, let's see, V over L will be equal to Zi minus, that was really bad, Zi minus Xi over Yi minus Zi, and this is our vapor-liquid ratio. And basically, this equation allows us to look at how the ratio of vapor to liquid changes over time as we increase or decrease pressure. So if we have a PT diagram, and we have our vapor and our liquid curves, and it looks something like that. And then obviously this is vapor, this is liquid, and then in here would be some sort of mixture. And we start off at a certain point, Z. Actually, I'll just call it Z, B, and or C, X, and Y. And as we increase the pressure over time, eventually we'll have our first drop of liquid to form. Our first drop of liquid will form. And that will happen at this point here, and we'll call that X, or we'll just, we'll put these in. So that's X, and that's the first drop of liquid, and it forms at a certain pressure. And we can look at the ratio between Z, X, and Y. And so if we were to keep going up this curve, and say we're at this pressure now, sorry, this is a bit messy. So here's our Z, our total moles. Here's our X. Here's our Y. We can see how the ratio between the distances from Y and X to Z change over time. So this would be X minus Zi, or more accurately it'd be Zi minus X. And this is Y minus Z. And as we keep going up in pressure, eventually we'll get to the point where we have all liquid. And at that point, our ratio will be 0 because we have all vapor, or all liquid and 0 vapor. And as you go up and down these curves, changing the pressure, it'll change at the same rate because we are following the same curves. The ratio It doesn't matter if you came from above and started at a really high pressure and came down to a really low pressure. At this exact pressure, these two ratios here and here will always be exactly the same at the same pressure. And this just lets us visualize how over time, as we're changing the pressure, it lets us visualize how the ratios will change and why bubble and dew pressure are so important to determining the outflows of a mixture or of a certain reaction, depending on how we change the pressure and the temperature.